Okay, so let's get started. Thank you all for coming. We have a bunch of panelists from for students at a bunch of different grades who attended the MIT PRIMES high school research program here in Boston. The program is for both math and computer science, but most students are, of course, doing computer science at MIT PRIMES. They're going to talk about their experiences in terms of what they did for their projects, what it was like as a social and kind of community, and also the applications process. And a lot of them worked individually, but also some of them worked as teams or in pairs, and so you get to hear about that as well. Let's do a round of introductions, starting with Betsy at the far end. Can you talk about where you went to school? When did you do MIT PRIMES? And also, maybe just like a one sentence of what your project was. Okay.
All right. Hey, I'm Betsy. I went to Lexington High School. I joined PRIMES in my sophomore year of high school, and in my PRIMES group, we studied computational biology. So more specifically, we studied genomics and how chromosomes fold using computer science.
Hi, I'm Leo. I went to Lexington High School. I did PRIMES for a year in sophomore year, and we worked on stuff related to cryptocurrencies and more specifically cryptographic proofs of work.
I'm Dylan. I go to the Newman School in Back Bay. I did PRIMES when I was a sophomore and a junior. And my project when I was a junior was, I guess the most concise way, it's like a generalization of binomial coefficients turning into polynomials, and you're looking at patterns of the polynomials.
Hi, I'm Sanjit. I'm a junior at Acton Boxborough, and I did PRIMES sophomore year, and I'm currently doing PRIMES. So my research is in applying website fingerprinting attacks to deceive the Tor network's anonymity.
I'm Ben. I'm in 9th grade. I'm not actually in PRIMES. I'm in PRIMES STEP because, like, I'm young.
So PRIMES STEP is the middle school.
Yeah.
Okay. Yeah. Yep. We also have another PRIMES STEP. We have to come in and talk later. Yeah. So.
Yeah. And last year, our project, like everybody at PRIMES STEP was in the same project, and it was on game theory, and we did chomp.
My name is Evan. I'm a senior at Lexington High School. I did PRIMES in sophomore year for 1 year. I was in a math reading group where basically we read a graduate level math text, and we created a presentation and project about it, and I read about knot theory.
Yep. So thank you very much. And one of the first questions that many people asked was, of course, what is PRIMES, but also kind of what is research in general. Research is fairly different from many other activities that middle school and high school students might do. For example, computer algorithm competition or hackathons, or even just doing class at school. So which of you, I guess, would like to talk about what it was like to do research, and also what your preconception, what you thought research was before you went in, and what it actually turned out to be, and some surprises along the way. Does anyone want? You know what? I'll call them.
Yeah, I can talk about it a bit. So I think PRIMES played a big role in just sort of changing my idea of research, because before I was like, oh, it's just going to be a bunch of like research, just something that's done by like all these like old men in like white lab coats, and they're all in these wet labs like with these steaming beakers or whatever. And I got to PRIMES, and I was really surprised when I first walked into my lab, and it was like these people are like young. They're people that are like me. They're like, we had a computational lab, so it wasn't actually a wet lab at all, and it was just like a room with computers, and you sit down and you search through a lot of data and you look for meaning there. I think it was really meaningful to me because I was like, wow, someone like me can actually push the boundary of science and push the boundary of human knowledge. It's not just like, it's something that like I can contribute to, and I think that was huge. I think the actual process of research was also something that Primes taught me a lot about, because it was a lot of just looking, like we have a lot of data and we're just looking through the data and trying to see, is there a pattern here? Does this have meaning? Does this connect to something else? And it's like looking for treasure, kind of, because you can go for a really long time, you can do all the right things and still you can get nothing. But it's for those times that you look and you actually find something, that the chance of that is what makes looking through all of that junk meaningful.
And then also, I guess, research itself is a grueling process at times, as you kind of just alluded to. Can some of you talk about how much time you spend there? What kind of schedule does it usually involve? When does the program start? When does the program end? That kind of thing.
I can talk about that a little bit. Something that they emphasize in like the orientation when they talk about primes, I don't know, wait to look, hi, is that you get out of it what you put into it. And so you actually could, I don't know, waste your time and not put much in. But like what Betsy said, yeah, it's a year-long program. And so, you know, the schedule is very, you know, adapted. There wasn't any like standard schedule that you have to adhere to. You get some mentor and you talk with them about what times you want to meet and when to work. And so it's very flexible. And
how often would you meet, do you say?
Probably weekly. I think it varies a lot from group to group or project to project. Sometimes, you know, these schedules, like they can have like month-long breaks if you want to do some class or something. And just something to add to what Betsy was talking about, it looked like you were searching for a word at one point. I think the word should be fun. It's very fun. It's not just like hitting your head against the desk trying to figure out what to do. It's very fun. Like the project I worked on for most of the time was actually breaking another researcher's scheme, looking for like inadequacies and ways that it broke down, and that can be very fun. It's just a fun process.
Cool. You mentioned mentors. Why don't we go down the line entirely and kind of talk about who you work with and to what extent you work with them. So ostensibly, some of you were paired with professors, but also I think a lot of you worked with graduate students, PhD, masters. So you know, who, and also other researchers of your own age, other high school students. So can you talk about kind of who you worked with and to what extent did you work with those people? And maybe we'll do it from this side.
Okay, so I work with a graduate student who went to Harvey Mudd College for his undergrad and was a graduate student in math. And I also worked with another high school student who was a year younger than me on the project.
So at staff, like everybody works on the same project, so we have like around 10 kids all doing the same project, and they're all just like kids who, yeah, they're all like my age.
I currently work with, well, so I'm in a group project, so my partner is also a junior at ABRHS, Acton Boxborough, and our mentor is a PhD student at MIT who's working in security, so his interests were aligned with our interests on this project, and that was one of the things that sort of kept us, kept both him interested and us interested. We got really into the project, and yeah.
So both of my years in Primes, I was working with a math PhD student, and
you did a math.
Yes. So actually, even though I did a math project, I actually found that a lot of the time I was using computer science because you have to deal. One of the things you have to do is you have to make conjectures. You have to figure out what's happening with your problem, and in order to figure this out, you need to go through a whole lot of data. So you need to be able to compute that data efficiently. So efficiency is a major thing, and you need to have fast algorithms to do this. And you also need to be able to organize it well. So both of these skills are really computer science skills, and they're kind of essential. And as for the meeting schedule, I was actually very regular with my mentor. We just met every single week at a set time. So
In Cambridge?
yeah, MIT every time.
I worked with a computer science, computer security graduate student at MIT. Yeah.
I guess my situation was a little different because I wasn't really working with one specific mentor the entire time. I was pretty much, my partner and I, she was also a prime student in my grade, we were basically just placed into a lab at MIT, and we had official mentors, but we were kind of just working with all the people who came in and out of the lab, the grad students there. We would touch base with the professor occasionally. The scheduling was really not regular at all, because sometimes we'd have like a week where both of us had time and we'd meet up and just go crank out a lot of stuff, and other times we'd like show up and everyone in the lab would be like in South America. So it was definitely like really flexible, and really, yeah, it was different from your situation.
Cool. One of the big differences, I think, between research and perhaps what you did at school, and I heard this from a lot of you beforehand, is that the kind of tools and languages you're using are, to put it lightly, a lot broader than what you use in a classroom setting. While in a classroom, if it's a computer science class, you might focus on one language or one area of math, for example. When you're doing research, you have to pick up multiple languages, different systems, and even have to do some tech out of that. So can we hear a little bit about what kind of were the tools that you used to do this research? And hopefully that will eventually segue a little bit later down, maybe 10 minutes from now, we'll talk about what the actual project was. But for now, what kind of tools did you use?
So in my research, so first relating to, I think, the first part of what you were talking about, which is that like how this differs from what you do in school. One of the biggest things for me was that PRIMES really emphasizes the creative aspect of doing science versus what you do in school, and even like a competitive programming contests or something like that. It's a different aspect of science. So the experience you get in PRIMES is a kind of a special one, because you're really supposed to open up your mind to this field that you're working in. And I think the most rewarding thing is immersing yourself in the field that you're in. And so for myself, I was doing research in applying artificial intelligence to cybersecurity. So I immersed myself a lot in AI, and I was able to like look at different research papers and try to get inspiration from there. And specifically relating to the tools that I used, I used Keras with TensorFlow for writing neural networks, and Python mainly.
Hear tools from everybody else as well.
So when I was trying to like just create data to make conjectures from, mostly what I was using was Sage, which is Python based. And I also use a little bit of Maple. Yeah, that's basically the computational aspect.
So I guess I was in computer science primes, and I actually had 2 projects. And so this gets to another nice aspect about primes, in that it is creative, and like you do come up with, it's not just a grind of work that, like in school, it's just given to you. So for example, I was in a group of 4 people for like 2 weeks. And then I came up with my own idea for a project to do. And I told my mentor about this. And so then I just branched off and did that project one-on-one with my mentor. And that project was like a implementation cryptocurrency type project that ended up taking exactly 3 months. And I used Python for most of the coding there. It wasn't really required to use Python. I specifically chose it because I wanted to learn Python. I didn't know any Python. And then after that, it was mostly theoretical work. And so there actually wasn't a lot of coding involved, because you were just trying to see theoretically like which parts does this like abstract scheme break down. Yeah.
Sort of going off of what I think Sanjit said earlier, it is really different from school. I think one of the things that I really liked about it was in school, they explain a concept to you, and then You can ask like why a lot of times. And then eventually you'll run into a wall where the teacher's just like, I don't know. And then you can go and like consult like internet and other things. But I think the interesting part of research was that if you keep asking why, then you go and like find the answer for yourself, and you find the answer that like other people didn't know beforehand. And that was really cool. Oh yeah, tools. So we used mostly Python in the lab. We used a lot of, but I felt like I was constantly having to pick up new tools and like new languages or whatever. We used C++ in some places. We used C in some other places. We used R in some other places. And then there was just constant like stream of Python tools like matplotlib, like one after another. I had to keep learning for basically every new thing I was trying to do, which was in one way difficult, but in another way pretty interesting.
So like being in a math group, I guess you don't really have like much coding to do. There's no like Python or Java or whatever. And yeah, as Zen sort of mentioned, there's LaTeX involved, which is like the extent of like the computer that's needed. But I guess even surprisingly for like just like a reading group, we also did like really go in depth, sort of as Betsy was hinting to, like just like keep asking why. And like we didn't just use like a textbook in order to like answer questions. We would like go on the internet and like Google like different articles to like sort of like understand the theory better and understand like the workings behind everything better.
So in my group, our project, like we didn't use computer science that much in it, but like the few things that we did use it for was like we modeled the game with a computer science language. Like I used Java, and then in that same week, because we didn't really communicate within ourselves, another student did the exact same thing except in C. So, and then yeah, like because our group was a lot larger than all of the other research groups, and we had like a more diverse skill set.
Now, one of the things as an audience member is it may seem pretty intimidating, the kind of tools and the kind of things that you have to do as part of your research. So that leads to the question of the applications process, what you need to do beforehand, and what you do before coming into PRIMES. So the MIT PRIMES application just came out. This year's computer science section is on radix trees, computer trees, for example. I think last year was on RSA, the year before that it might have been on several automata, the year before that they did a custom coding or something like that. But I think a lot of people are intimidated because they think, oh, I need to have learned all of this stuff before I even have a chance of applying. So maybe some of you can talk about what it was like to apply and what kind of prerequisite knowledge you think you need before doing this kind of program.
So I don't think you really need that much prerequisite knowledge. What you need to be is curious and self-motivated. So like on the problem set, you're allowed to go through and read stuff if you want to. So if there's a question and there's some theory you don't know, you can like read through introductory texts or something and get a feel for what's going on. And even going into a research group or a reading group, your mentor will, if you don't understand something, your mentor will provide you texts and they will explain things to you so you can get to a point where you can do research. So I think the most important thing is like your attitude going in. You need to be really self-motivated.
Yeah, sort of to add on to that, like I'm kind of one like the type of kid who does like a lot of math contests. Like that was kind of my basis before going into PRIMES. And even though this was the case, I really didn't feel like it was necessary for me to know a lot of like the contest math things that I did know. It was really more just I kind of had to like sit there and think about the problems and like kind of as Dylan said, like look for like different things that I hadn't even encountered before. And it really doesn't have a lot to do with like, at least for the math section, it doesn't really necessarily have a lot to do with what you know beforehand or like the types of math projects you did. It really just takes like dedication and just like thinking about the problems.
And also, I guess, what is the actual application like for those people who haven't seen it?
So for the computer science application, you have to fill out computer science problems and general math problems, and then you have to write essays, get letters of recommendation, and I think that's generally it. So specifically relating to the computer science problems, the programming knowledge you need is quite, I'd say it's quite basic. So you don't need to like code up really large projects or anything. I think the main thing, at least when I filled out the application, is you need to immerse yourself in the problem set. So last year it was on RSA and public key crypto, and whatever the problem set is, you just got to immerse yourself, and you can consult other resources like online. If you don't understand something, then you can consult those resources. But immersing yourself and trying different methods of solving the problems usually leads to some level of success in the problem set.
Yeah, to go off of that, the PRIMES application, it gives you a lot of time to do things. So if there's something you don't know in it, as long as you give yourself the time, you can go out and learn it. I think I actually first applied to PRIMES my freshman year, and I didn't make it. And this was because I went in with the expectation that it would be like sort of the other P-sets and like math things I've done before, where if you have the right knowledge, you can just get to the answer real quick, bam, we're done. But then I got the PRIMES application, and I was like, wow, you actually need to think about these for a long time. And I was...
Quantify a long time. Is it like 7 hours, 10 hours, several weeks, several months?
It's not like you just plop yourself in front of it and then like wait and the answer comes to you. I think they're like, I don't know. I could not imagine myself just sitting down for 7 hours and researching it. I needed time to like just learn various things over the course of like a span of multiple weeks. I also, because for each step I had to like explore things, fail at them, try different things, learn new things in order to try the new things. It's just a very, they design the problem set well because well in a way that it sort of forces you to do your own mini research in order to get there, if that makes any sense.
For me personally, what I found, like when I was looking at the problems on the problem set, like the general problems take a much smaller amount of time than like, the advanced problems, at least for the math section. So the general problems are what you have to do if you want to apply to computer science as well. But if you're doing math specifically, you need to do the advanced problems too, or at least attempt them. So like for the advanced problems, you could easily be like a month or two on and off thinking about it before you finally figure out what you're supposed to be doing.
And you mentioned general problems, so it's not obvious, but even though it's applied to the computer science, PRIMES have to do the math problems as well. Okay, let's talk a little bit about your actual projects. And some of you, I think, included some pictures beforehand I can show. Some of you can just talk about it. Does anyone want to go first about what you actually did?
Yeah, sure. Yeah. Do you want? I sent 4 slides. Let me see.
Betsy, do I have one?
Yeah, I forwarded it.
I don't think I got it. Why don't you talk while I chat?
Yeah.
Does it look like anything that we have to do?
No, it doesn't.
Okay. Okay.
So my project is it's in the area of cybersecurity. So my project is in the area of cybersecurity, and specifically we're analyzing. We analyze the Tor network. So the Tor network is the most popular network for anonymity and anonymous communications. So many people when they're suppressed by an oppressive government, they might use the Tor network to gain anonymity. So our project was twofold. First, we worked on attacks on the Tor network, so deceiving user anonymity. And then second, we worked on defending against these attacks that we created, and making the Tor network more secure while still being usable enough. So the Tor network works by routing users' information through multiple different chains or servers before it exits the network. So it usually, like a user might be able to know who the sender and receiver of of someone's information is, and on the regular internet, they know that information, so they can deceive anonymity. So on the Tor network, it hides this information by routing it through multiple servers. So, but there's this attack called the website fingerprinting attack, and in that attack, an adversary who just sees a user's packet information going back and forth, they can form a fingerprint of the packets going back and forth and correlate those packets with the specific website. So, for example, if they saw 512 bytes worth of information consistently going from a user to a website, they might know that website is Google. So they can correlate information and deceive a user's anonymity. So in my research, we worked on improving the state-of-the-art attacks and also creating defenses that are both secure and efficient and deployable in the real world.
I think I just finally got it. Yeah. There you go.
So yeah, these are slides we used in the PRIMES conference. So the first one is just showing that anonymity matters. So like whistleblowers, government suppression. The second slide is just showing how in the regular internet, anonymity is not guaranteed because an adversary in the middle can determine the sender and the receiver. The third slide is showing how the Tor network works. So it routes information through three different servers, and it's supposed to provide anonymity that way. And the fourth slide is showing how an adversary looking in to the Tor network, and like say in Alice and the first Tor node, can actually correlate the information going from Alice to the receiver and correlate those packets with the specific website Alice is connected to.
Okay. Thank you, Sanjay. And because we're going over student projects, if you're online or on one of the chat platforms that we're conversing over today, you can ask a question. So if you're on the GoToWebinar, for example, there's a question box that you can use to ask a question. And if you're on the WeChat, you can send us a message and we'll forward it to the panelists. So if you have any questions specific to them about their project, now is also a good time to ask them, and I'll forward them during the course of it. But who wants to go next? Okay, go ahead, yours, or just on.
Betsy didn't tell me to send any slides in.
Okay.
But it's okay, because I didn't have any slides anyways. Yeah, so I'm only going to talk about my second more relevant and more recent project, which it was, I'll talk a tiny bit about how cryptocurrencies work, but cryptocurrencies are a decentralized kind of currency, and if you just want to say, you know, send money from someone to somebody else, it's kind of like you're literally writing a message, I send this much money to somebody else. But if I just say, like, write to some public ledger, this is how, for example, Bitcoin works, that I've sent this much money to somebody else, and then they send you some package, I don't know, maybe you bought a water bottle. That's not the best guarantee, because at any moment something could happen to that message or somebody could erase it. So you need some special cryptographic way to secure it. And the part of that system, which I won't go much into, of cryptocurrencies is called mining. And the way it works involves these things called hash functions. For Bitcoin, it's called hashcash. And so when people are setting up a cryptocurrency, they have to choose the mining function or hash function for their cryptocurrency. And so what brought up our project is that this startup, newer cryptocurrency called Zcash, which actually doesn't do exactly the ledger thing, it does something much more complicated using zero-knowledge proofs, chose to use as their proof of work, their hash function, recently proposed thing called equihash. And the thing is, a lot of things around equihash seemed kind of sketchy. And in a first read of like the paper that the two cryptographers wrote on proposing this thing, you could already see that there are some places where proofs broke. And so what we did is we want to look into, what were the implications of the false analyses here, and what are some ways we could propose to fix it. And so, for example, one of the implications of the work is that you have to choose tuned parameters that's right for the cryptocurrency, and it seems like that basically Zcash, they already launched, and it seems one of the implications, it seems like maybe they didn't choose the best parameters, and so that hurts the cryptocurrency in a big way. So most of the work there was kind of mostly theoretically looking at the work and other papers related to see what we could do. And we also proposed another hash function that has some other issues but fixes some issues in equihash.
Now, stepping back a little bit, so does this, you didn't bring slides today, but presumably you had to write something about this paper.
Yeah.
Once you did this research, how was the paper submitted, or was it posted somewhere?
Sure. That was actually very recent, that just this last summer, that we finally wrote up the paper, and we submitted to a cloud computing security conference, and just I think maybe less than a week ago it was accepted. And so sometime in November I have to go into Dallas to talk about it. And so I will have to make slides for that. And that process is actually pretty, I found I'm not the best writer, I found the writing up of it very difficult, but to actually submit is nice. They have an anonymous review process, and so you submit your paper with anonymous authors on top, and then they send it to a couple of reviewers who are knowledgeable in the field to read over your paper, make some comments, and actually comment on whether they think the conference should accept the paper or not. And that whole process is mostly you send it out, then you wait a month and just hope it gets accepted. And if it does, good. And if it doesn't, you look at the comments and make various edits or look into things again and submit to some other conference. It's very common that you have to submit to a few conferences at first for it to actually get accepted.
Okay. Who else wants to talk about their project?
I'll talk about mine. You have some images that I sent you.
Well, we can start while I type that.
Yeah, so my project was about Q-binomial coefficients. Sometimes these are called Gaussian polynomials too. It makes it a little bit, my project title, a little bit less confusing because it's called coefficients of Q-binomial coefficients, and people might ask, what's a coefficient of a coefficient? Well, the answer is that a Q-binomial coefficient is not a number, it's a polynomial. So you can talk about a coefficient of it. So I think there should be a second image there. Yeah, that one.
Okay. X.
Can we make that bigger? Is that possible? Yeah. Okay. So binomial coefficients count ways to find subsets of things. What Q-binomial coefficients do is slightly different, but they actually generalize them. What they do is they count what are called subspaces. So these, if you plug in Q equals 1, you can see it's a polynomial. It'll actually turn out just to be the regular old binomial coefficient, which is pretty cool. So what I was studying is what happens when you take this polynomial and you look at each coefficient and you look at it modulo some number n. So like say you have 5 and you're looking at it modulo 5. That means you subtract as many copies of 5 as you can, and keeping it positive. So you turn that polynomial and you have a new polynomial. It has all these coefficients, and the coefficients range from 0 to 4 in this case. And the question that I was looking at is how many of each residue, numbers 0 through 4, are there? And it turns out there are some nice patterns with this. And the reason you would expect something to be there at all is because you can notice that the sum of all of these, sum of all the coefficients is equal to the binomial coefficient, because when you plug in Q equals 1, it's equal to the binomial coefficient. And we already know a lot about binomial coefficients when you do the same modding out thing. So we would expect there to be some sort of pattern when we look at the coefficients of these polynomials. So third picture, the one with all the dots.
Third one.
Yeah.
The one that I had open earlier.
Yeah. So when you figure out what this function is, the function that describes, says you have a Q binomial quotient and choose K or something, and say you fix K and you look at it as a function of n, and you're trying to figure out how many residues of each type there are. It's just a bunch of linear functions put together. So that's a graph of all the slopes of these linear functions. You can see there's a whole bunch of patterns here. So that was one of the things I worked on. So it's like lots of symmetry here. There's sort of different levels, so you can talk about all of these sorts of things. That was what my project focused on. And proving that they're linear functions too. That was the main result because that was the conjecture.
Cool. Let's go next.
So we can talk about mine.
Did you get slides for me or?
I sent in the paper. Okay, it should be. So basically, I was in a reading group, so we didn't really have like a research question of any sort. It was really more of we kind of did like a slight overview of knot theory in general, I guess. But for the presentation itself and for the paper itself that we wrote, we decided to look at a specific property. So basically, it was defining the Jones polynomial for knots. So basically what we did was we sort of introduced knot theory and sort of defined what a knot was, and then we talked about how we could create knot diagrams and then thus create knots as in terms of graphs. And if we could do that, then we could express it in terms of a polynomial. And it's honestly been a really long time since I've looked at this, so I don't really know how to do this anymore or what I'm really talking about. But yeah, since we were a reading group, we didn't necessarily go super in depth into any of this. It was really more of we kind of just took an interesting property of from knot theory and just discussed some of the results that come from it.
Yeah. What was your favorite part of knots?
I was allowed to make a very petty point. Well, my favorite part of the PRIMES experience, honestly, for me, was like discussing like other math topics with my mentor that wasn't really related to knots, and kind of like just being able to come to him with like different math questions that I had from like math competitions that involved like group theory. But yeah, that's also cool.
Okay. You want to go next?
Okay.
Okay.
Yeah, so again, my PRIMES group was in computational biology. So what we were studying was chromosome folding. So
I'm just gonna that. I'm just gonna do the email. Okay.
okay. So basically, so there's been a lot of research into like DNA and like what the significance of like the actual code of the DNA is, but there's been a lot less work. There's been a lot less research going into what is the significance of the structure of the chromosome, because obviously you have the actual encoding of the DNA itself, but then you have the way it folds, which is this really complex process, and it forms all these weird shapes. So what we did was we looked at the different certain features that would appear when chromosomes fold and try to see if this had any meaning in terms of the function of the DNA. So maybe this sort of structure is correlated with gene transcription. Maybe this sort of feature is correlated with gene regulation. And so we wanted to basically discover what significance the structure of the chromosome had, and using that, try to gain more insight into how these actual functions themselves worked. So the way this happened was we took a bunch of data that was like, this is how. So we basically took a heat map of the chromosome, in which between any 2 points you have a frequency of how commonly they're touching. And then using that data, you can sort of imagine what what their like relative distance would be most of the time. This also gets a little more complicated because things move around all the time. But we took those features and we basically compared them to a lot of other data sets that were generated, like protein concentrations in the genome, and say like chromatin state, which is like basically people characterize different parts of the genome as these different categories. So we would compare these categories to the frequency of, basically we would look at the frequency of each category of DNA that would appear at these certain features. And basically, after a while, we were like, okay, so it looks like this certain feature, which forms like a loop structure, we think it's pretty heavily correlated with gene regulation. And this other thing that's called like a domain, which is kind of like a blob of DNA, seems to be correlated with gene transcription, so just like transcribing the gene.
We have one question from someone online which says, presumably to all of you, how did you select the project subject area? Like, how did you get to choose, I want to do biology or I want to do security or whatever?
Well, I didn't. I think most of PRIMES projects are assigned, correct me if I'm wrong. Okay. But yeah, I applied for computer science, and then computational biology is probably a subset of computer science in PRIMES because I got assigned to a computational biology group. At first I was like, oh crap, I don't actually know any biology, so this is going to be really bad. But they ended up teaching me a lot on the spot there, and it was a very specific subset of biology that you probably wouldn't have learned otherwise anyway. So that was really cool.
For me, like on the application, you indicate some of the things that you're interested in, and I think what they do is they just pick one of these, and then they ask around professors that maybe in this area for questions, and then they give you a question.
Cool. Okay, and then what about this? Did you, we two STEM people, right? Were you guys on the same project? Or? Okay, can you speak a little bit about your project again? Like, I know you mentioned a little bit of it before. But yeah.
So my project was about game theory and specifically Chomp. So it's like, it's a game, it's a two-player game where you have an n by m rectangle, and every turn one player can take or choose to chomp, as it's called, another a by b rectangle out of the original one. And then there's two versions of the game, one where you don't want to take the last square, and one where you do want to take the last square.
It's like a two-dimensional game, I guess.
Yeah. And so that problem was actually too hard for us. So we did a version of that which we called Diet Chomp, where you could only take up to 1 by 2 rectangles out of an n by m. And we ended up, like, as I said before, writing computer programs to play the game, basically. And then we also, like, we made graphs showing, like, this position will make, like, if you have this position, then you can win. And if you have this position, you can lose, or the other person will win. And, like, with those graphs, we actually try to figure out where they stabilized, because at the beginning, like, the graphs didn't seem to have any pattern, but as you kept doing it with larger numbers, then they a pattern started to emerge, and that's what we call stabilizing. And we wrote a paper about that.
So presumably you made also a program that you couldn't beat, or potentially couldn't beat.
Yeah.
Okay. Do you want to talk a little bit about what project you did?
Yes.
You're not here. Yeah, I guess you're like.
Hello, I'm Kevin Zhao. And I'm from MIT Prime Steps. I'm in 8th grade right now. And for our MIT Prime Steps course, what we did was we just decided to like come up with different games and like search them and see if we can solve them. We ended up coming up with a couple of games. for example, like a game where you had like a diamond of dots, and you had to take rows and columns out, and the last person who took out a row wins. We also did a few other games. It was a little different than Chomp.
Great. So that pretty much completes the project, right? Okay. Did anybody have questions specific to the projects? Okay. So we are at 8:05 right now, and I want to give the audience, the live audience and the online audience, a little bit of a chance to raise their hands if they have specific questions. So does anyone here have any questions that they'd like to ask the panelists? Or anyone online? I have one question online, which is like, can I get a recording of the seminar? And the answer is yes.
Good question.
Okay. In light of no live questions, then I guess I'll ask a couple for you guys. One is, I guess, something that I don't think anyone answered before, but can you do MIT Primes for multiple years and doesn't have to be the same topic?
Yes, and it does not have to be the same topic.
Okay.
You can like specifically request, like if they put you a comment
For example, and for my MIT Prime steps, we're doing different topics this year from last year.
Okay. And I guess the last thing I wanted to talk about is kind of the community and the environment of being there. Like, what was it like to meet new people? What kind of friendships did you make? Even not what kind of friendships, what kind of new people that you previously wouldn't have been exposed to, what kind of events you did, that kind of stuff. So, does anyone want to talk about that for a little bit?
So like for me personally, like as I kind of mentioned before, I like definitely did like a lot more math contests before, and I'm like very heavily, like especially early in high school, I was very heavily involved in like that sort of community. Like I went to like a math camp in like 8th grade and also the summer of 10th grade, and they were like, and I think the way I describe Primes is like the people there definitely like take themselves more seriously, I guess, or like take their projects more seriously, and like definitely like much more involved in their projects, and like yeah, it's like definitely like a good environment to be in, like if you're like really into like doing research, and like if you really like do find a passion for doing research, like you'll find like definitely a group of people who share that passion, and it's like definitely more, yeah, like just like compared to like other like people who are like also like good at math, like and like a math competition sense, like I definitely felt like people there definitely more like not like mature but like serious. Yeah.
Community friends? I know you guys did, but like, lots of context.
So for me, my partner was in my school, so we were already good friends before we became partners in the Primes project. But one really interesting aspect of Primes is that you get to collaborate very closely with someone who's working on the same problem as you. So for us, we were actually working on two like sort of adjacent paths, and we combined it into one research paper, which we're actually submitting to Siemens tomorrow. But like but you get to work very closely with someone else, and it's really it's very fun, and also a good like mental exercise to have that person to bounce back ideas, like to bounce ideas from. And one other thing about Primes is that in your research, you get a lot of independency, especially with our project. We ended up getting a lot of independency in that what we did for the May conference was drastically different from what we pursued in the summer, and we were able to just like look in the field and see what we wanted to do, and abstract out from what we were doing in the conference. And in the end, like we were able to take ideas from multiple different fields and just like keep on working and pursue like a good overall product, I guess.
Yes, sort of similar to that. I think a really cool thing about Primes is being able to sort of participate in a lot of excitement, because you're working with people who are like on the cutting edge, and then you're around people who are like, they'll be staring at these numbers, and then they'll just be like, oh my god, that is so weird, and then you can go like grill them about it. But they just get, no, they're just so interested about these things, and you can see the way they look for patterns. I was mostly working with like the grad students in my lab, so you can see the way they ask questions, see the way they look for patterns, and like the way they look for sort of discrepancies and ways things connect, and then just how hyped they get about it. It's really cool.
Okay. One question somebody had was, do you guys get to use Java as well, not just Python? I mean, one of you mentioned Java. He says specifically, is there an option to use Java if I prefer to use Java?
You can use, in most cases, whatever language you want to do. Like, I used Java to actually generate some data for something. And like Sanjit just talked about, you have a lot of independence and stuff. And so if you want to do something your way, chances are you'll be able to do it your way.
Okay.
Yeah, sort of going off of the thing earlier I was talking about. One other thing is the Primes. Joining the Primes community kind of connects you to a larger community of like researchers, of people working on science or like math or physics. Like through my Primes lab, I got to go to things like the LIGO Gravitational Waves Conference when the people came to Cambridge. That was really cool. They're like, I would get all these notifications of like talks or just like news going on. Like the lab, I'd be part of the lab's conversation when they'd be like, oh, check out this thing that happened in like Siberia. That's like cool science.
Okay, so maybe two final questions before we wrap it up. It's almost 8:00, right? Okay, we have a last question.
So what's your name to Primes? Does it like take a lot of time for you to like get started, or does it just sort of go in there pretty easily?
So you're asking,
so like how hard is it to like get started in the research?
How hard is it to get started in the research? It's actually very similar to a question online that asked, what computer level of proficiency do you need to be able to work in a Primes project successfully? For example, would you need to pass the AP or something like that? So yeah, I guess the question is kind of how hard was it, and how much. We talked a little bit about what kind of prerequisites you need to have, but like, is it okay if you don't know how to write an if statement, or do you need to have 13 years of computer science experience? Can some of you kind of draw a line as to what rough area of prerequisite knowledge you need?
If they let you in, you probably know enough. Like if you can get along with the problems all right, and you don't have to get all the problems. Like you definitely, I don't think it. Well, maybe somebody here got all of them, but I didn't. Yeah. So.
And I guess just a ballpark. I guess I'll answer it in a part. Most of these problems we find at KTBYTE are a similar level of difficulty as to the data structures and algorithms level courses that we have. So. This is not usually the, I know just how to write an if statement and for loop and an array and a function kind of level material. This is usually, I've worked with linked lists and array lists and building linked lists and making trees and making graphs. And I've done maybe a use code contest at the bronze level or two. Maybe I haven't passed. At minimum, I've tried that kind of level material. So it's not trivial by any means. And one of the people are asking online kind of how competitive it is. Can someone tell me roughly how many people are participating in MIT Primes?
I think it was like around 50 people.
Yeah,
I'd say,
that sounds great.
Yeah,
It's
around
20 in that section.
Yeah, around 50 people, and there's a fair amount of people who apply also. But I'd say in terms of the CS application, the prerequisites you need, the most important part probably, and this is where experience helps, is in your problem-solving skills and your logical reasoning ability. So the comp sci problems will, so when I applied, it was RSA. RSA, you won't see that in many courses you take, and also in USCO or something like that. But really, by taking USCO and solving a lot of problems, working on projects outside of before the application, it'll build your logical reasoning ability and your problem solving ability, and that way you're better prepared to solve the CS problems in the application.
And for MIT Prime steps, there's around like 80 people that applied last year, but there's probably more this year. And last year for MIT Prime steps, like there was like 20 or so kids in the program, like sort of like 21 to 24 each year.
Thank you. I had one student ask online if you have a silver the USCO, what are your chances of being accepted for Prime? I guess it's not so clear cut, right? So I guess the answer to you would be depends on also a lot of other things, not like your application essay, your recommendations, that kind of stuff. Well, not just pure algorithm knowledge. One question we didn't get today, but usually gets asked, is what's the benefit, both direct and intangible, of participating in this kind of program? Some of you have already kind of alluded to how it's improved your problem-solving skills, how it's improved your ability to reason about things that you might not know about. I'm sure some of the parents are thinking to themselves, does this have a direct application towards something in the pipeline of future activities for our child? So can someone speak to how they think both the experience and the pedigree of MIT Prime is helpful?
Okay, so for me, like, I kind of feel like it's like a good program for me to like sort of realize that I probably like didn't want to do math research in the future. Like, I was like a sophomore when I did it, and I discontinued junior year. I think it gave me like a good introduction into like what research would look like, and I thought that I might be like a person who might want to do that, especially because I was like, I'm like, yeah, like I was like, I think I enjoyed doing math, and that it was something that I might enjoy doing in the future. But I kind of realized, I guess, that I didn't necessarily like have like the patience maybe to like really go in depth with a lot of these topics sometimes, and sometimes they're just like much more satisfying to me just like problem solve on like these math competitions, and maybe in the future do something else. So I think like for me personally, Primes gave me like a good introduction to what it might be like to do research in the future, and definitely for other people too. Like if you want to do research, it's a great resource to like connect with like kids all across the country, kind of share that passion, and it's like a great starting point to like already like start like doing research and writing research papers. And it's great if you want to like do it later in life and in college, and yeah, just in life in general. But it also like for me gave me like a good
yeah, there are a lot of people who go into Primes and then they're like, yeah, I really like this, I really want to do research with my life, and then they're already in a place where it's a very good point to jump off because they know the people that are already in the lab, exactly what he described.
And when you get into Primes step, you might get into like Primes too. You have a better chance of getting into Primes because like the professor that teaches Prime steps could give you a recommendation letter.
Beyond Primes preparing you just for doing research or going into academia later in life, the main thing I'd say that Primes prepares you to do is to put like a very long period of time, spend a very long period of time working on one specific problem, and the ability to have the patience and the persistence to do that and spend a ton of time, like 10 to 15 hours or sometimes 20 hours a week, and throughout basically the entire year on a single problem, and going through like failures, multiple failures, and finally having something that succeeds in the end. Like that ability is I think quite important in several areas, future areas of life. So yeah.
And that's something that you often, like if you only go to school and you only just like do homework and assignments, it's not something you get so much from that process. Like when I went to Primes, it was definitely really new to me.
And I would second that point about patience. Like for my project, 95% of the time I was stuck. And like, I didn't know how to do this. I've already tried 10 different approaches. What do I do now? You have to be really patient, and you can't magically expect to see the solution to everything. You might find it in the end. That's only after you tried bunches and bunches of times and failed bunches and bunches of times.
Okay. We're pretty close to the end. It's been an hour. Any final questions before we wrap things up?
I have a question about the PRIMES maths.
Okay.
So normally, do you have to get like a very good contest, like a win on the math contest to get into the program? So you don't have.
No. So I don't have like any contest background at all.
And maths.
Yes.
But you have to do you have to finish the entry test.
Yeah, so if you do very well in the entry test, so I think what they look for either you have a math contest background or you've been to one of these math camps. So I think I have been to one of the math camps, and I think that made up for the lack of contest background for me.
So like sort of add on to that, the group of people who do math contests, the group of people who end up going to math research is actually like not as, the interest actually is not as large as you might think. There's definitely some kids that I know, at least like a couple of kids that I know that go to MIT right now who like did contest math and like very like proficient in contest math and like got into applied math and like sort of like realize they don't really want to do research math, and like the settings are very different. Like both require like a lot of hard work, like both require like you to like sit down and like think about things. But like for contest math, like you can definitely like think about like more things. There's like more things that you can explore and like sort of think about. Whereas with math research, you really got to like think about like a couple of things like very in depth. So like those two are like, I mean, you should probably have some sort of math background. You should definitely be interested in math in some sort of way, but like math research and math contests are like very separate in that sort of regard. Where, yeah, one's like very in depth, the other one's like in depth, but like maybe not as much, but like encompasses a lot more.
But the contest experience can't hurt.
I think there's a question over there.
The deadline for application, someone was asking, I think that's December 1st. I was showing that earlier. Yeah, December 1st is the application deadline.
Don't wait until the end of November to start.
Wait until November. Oh, the test deadline? I actually don't know.
It's like an entry test on.
It's not like a problem set. You just show up and then they give you a test and you do the test like at MIT.
Okay, do you know what that is? Okay, yeah, the deadline is May 31st, 2017, so that's super duper over for prime set. Yeah, the next year. Okay, anything else? Well, let's have a round of applause for our panelists. Thank you for coming. As stated, we'll have a recording of this online and available for the online audience. And you can also email us or message us questions afterwards, and we'll forward it along. Thanks for coming. Bye-bye.
Bye.